Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss vacuum systems and steam ejectors. The converging-diverging steam jet is a startlingly complex device. Not only is the theory of operation rather weird, but the jets are subject to a wide range of odd, poorly understood, and never reported malfunctions. For all these reasons, we rarely love to retrofit and troubleshoot steam jet systems. Steam jets have been around for a long time. They have just as ancient an origin as do steam-driven reciprocating pumps. They were used on early steam engines to pull a vacuum on the now archaic barometric condenser. More recently, they were used to develop vacuums in such services as surface condensers that condense the exhaust steam from steam turbines, petroleum refinery crude residue vacuum towers, flash evaporators used to produce concentrated orange juice. Steam jets are also employed to recompress low-pressure steam to a higher-pressure steam. Jets are sometimes used to compress low-pressure hydrocarbon vapors with higher-pressure hydrocarbon gas instead of steam. They are really wonderful and versatile machines. Theory of operation. The converging-diverging steam jet is rather like a two-stage compressor, but with no moving parts. A simplified drawing of such a steam jet is shown in picture. High-pressure motive steam enters through a steam nozzle. As the steam flows through this nozzle, its velocity greatly increases. But why? Where is the steam going in such a hurry? Well, it is going to a condenser. The condenser will condense the steam at a low temperature and low pressure. It will condense the steam quickly. The steam accelerates toward the cold surface of the tubes in the condenser, where its large volume will disappear as the steam turns to water. The motive steam accelerates to such a great velocity that it can greatly exceed the speed of sound, that is, exceed sonic velocity. This tremendous increase in velocity of the steam represents a tremendous increase in the kinetic energy of the steam. The source of this kinetic energy is the temperature and the pressure of the steam. The conversion of pressure to velocity is a rather common, everyday phenomenon. Remember Hurricane Opal, which struck the Florida Panhandle in October 1995? It had peak winds of 145 miles per hour. The pressure in the eye of the hurricane was reported at 27 inches mercury. A portion of the kinetic energy of the wind in a hurricane is derived from the barometric pressure of the atmosphere. The lift that helps an airplane fly is also a result of the conversion of barometric pressure to velocity. Because of the shape of the wing, the air passes across the top of the wing at a higher speed than it does below the wing. The energy to accelerate the air flowing across the top of the wing comes from the barometric pressure of the atmosphere. Hence, the air pressure above the wing is reduced below the air pressure underneath the wing. Similarly, as the high-velocity steam enters the mixing chamber shown in picture, it produces an extremely low pressure. The gas flows from the jet suction nozzle and into the low-pressure mixing chamber. The gas flows into the mixing chamber because there is a very low pressure in the mixing chamber. The rest of the jet is used to boost the gas from the mixing chamber up to the higher pressure in the condenser. This is done in two compression steps, converging and diverging. Converging compression or sonic boost. When an airplane exceeds the speed of sound, we say that it breaks the sound barrier. In so doing, it generates a sonic wave or pressure wave front. When steam and gas flow into the converging section of the jet diffuser shown in picture, the same thing happens. The gradually converging sides of the diffuser increase the velocity of the steam and gas as the vapor enters the diffuser throat above the speed of sound. This creates a pressure wave front or sonic boost. This sonic boost will multiply the pressure of the flowing steam and gas by a factor of perhaps 3 or 4. Note something really important at this point. If for any reason the velocity of the steam and gas falls below the speed of sound in the diffuser throat, the sonic pressure boost would entirely disappear. Diverging compression or velocity boost. As the steam and gas leave the diffuser throat, the flow then enters the gradually diverging sides of the diffuser. The velocity of the steam and gas is reduced. The kinetic energy of the flowing stream is partially converted to pressure as the steam and gas slow down. This increase in pressure is called the velocity boost, which will multiply the pressure of the steam and gas by a factor of 2 or 3. While smaller than the sonic boost, the velocity boost is more reliable. Even though the velocity in the diffuser throat in picture falls well below the speed of sound, the increase in pressure in the diverging portion of the diffuser is only slightly reduced. The overall pressure boost of a steam jet is obtained by multiplying the sonic boost effect times the velocity boost effect. The overall boost is called the jet's compression ratio. Vacuum measurement. We have discussed the American system inches of mercury in my video, How Instruments Work. Of more immediate interest is table. To do any sort of vacuum calculation, we need to convert to the absolute system in millimeters of mercury. Unfortunately, we also need to correct measurements made with an American type inches mercury vacuum gauge for atmospheric pressure. You can interpolate between the two sets of data in table to correct for almost the entire range of typical atmospheric pressures. We will need to use this table to calculate a jet's compression ratio when we measure vacuum pressures with an American type inches mercury gauge. Compression ratio. When considering the performance of a vacuum jet, we must first consider the jet's overall compression ratio. To calculate a jet's compression ratio. 1. Measure the jet's suction pressure and convert to millimeters of mercury, as shown in table. 2. Measure the jet's discharge pressure and convert to millimeters of mercury. 3. Divide the discharge by the suction pressure. This is the compression ratio. It is not uncommon to find a proper jet developing an 8-to-1 ratio. More typically, jets will develop a 3-to-1 or 4-to-1 compression ratio. Any jet with less than a 2-to-1 compression ratio has some sort of really serious problem, but not necessarily with the jet itself. Jet discharge pressure. The jet suction pressure is a function of the following factors. The overall jet compression ratio. The jet discharge pressure, as shown in picture. The jet discharge pressure is controlled by the downstream condenser pressure. The minimum condenser pressure corresponds to the condensing pressure of steam at the condenser's vapor outlet temperature. For example, let's say that the condensing pressure of pure steam at 120 degrees Fahrenheit is 80 millimeters of mercury. If the condenser vapor outlet temperature is 120 degrees Fahrenheit, then the lowest pressure we could expect to measure at the condenser vapor outlet would be 80 millimeters of mercury. Let's further assume that the pressure drop from the jet discharge through the condenser discharge is 10 millimeters of mercury. The jet discharge pressure would be 90 millimeters of mercury. Let's also say that the sonic boost is equal to 3.60. The velocity boost is assumed to be equal to 2.5. The overall compression ratio is then 3.60 times 2.5 is equal to 9.0. The jet suction pressure is then 90 millimeters of mercury, divided by 9.0 equals 10 millimeters of mercury. While I have seen steam jets develop compression ratios of 8-to-1 or 9-to-1, the majority of jets do not work nearly as well as that. Multi-stage jet systems. A single jet that discharges to the atmosphere or to a condenser operating at atmospheric pressure is called a hogging jet. Let's assume that atmospheric pressure is 29.97 inches mercury or 760 millimeters of mercury. Also, we will assume the jet is capable of an 8-to-1 compression ratio. The jet suction pressure would be 760 millimeters of mercury, divided by 8.0 is equal to 95 millimeters of mercury. Referring to table, this would mean that the jet inlet pressure was 26.2 inches mercury on an American-type vacuum pressure gauge. This is about the best we could expect with a single-stage jet. Picture shows a three-stage steam jet system. Let's first calculate the overall compression ratio for the combined effect of all three jets. Note that the atmospheric barometric pressure is 26 inches mercury. This is a chemical plant in Denver, a mile-high city. The first stage jet gas inlet pressure is 25 millimeters of mercury. The third stage jet discharge pressure is 3 psig. A good rule of thumb is 1 psi equals 51 millimeters of mercury. The actual barometric pressure can be converted to absolute millimeters of mercury, using the following rule. 1 inch mercury equals 25.4 millimeters of mercury. Therefore, the barometric pressure in Denver is 26 inches mercury times 25.4 is equal to 660 millimeters of mercury. The pressure at the third stage jet discharge is then 660 millimeters of mercury plus 3 by 51 millimeters of mercury equals 812 millimeters of mercury. The overall compression ratio is 813 divided by 25 is equal to 32.5. But what is the average compression ratio for each of the three jets? Well, let's assume that the pressure drop for the first two condensers in picture is 0. Then let's remember that when compression stages work in series, their compression ratios are multiplied together to calculate the overall compression ratio. Then the average compression ratio per jet is cube root of 32.5 equals 3.2. We take the cube root of the average compression ratio, because the three jets represent three compression stages working in series. In this calculation, I have made a potentially serious omission. That is, I have ignored the pressure drop through the interstage condensers number 1 and number 2. Typically, these condensers have a shell-side delta P of only a few mm of mercury. Thus, their effect may be ignored. However, if these condensers are fouled, or if they are suffering from condensate backup submerging the bottom edge of their internal air baffles, then their delta P might be 50 plus mm of mercury. Such a large pressure loss must be included in the above compression ratio calculations. For example, the inlet pressure to a first stage jet is 20 millimeters of mercury. The inlet pressure to a second stage jet is 100 millimeters of mercury. The delta P across the interstage condenser is 60 millimeters of mercury. Then the compression ratio of the first stage jet is 100 millimeters of mercury, plus 60 millimeters of mercury, divided by 20 millimeters of mercury. This is 100 plus 60, divided by 20 is equal to 8.0. Jet performance curves. I have rather implied up to now that a steam jet, depending on its mechanical condition, will develop a fixed compression ratio. This is not true. For one thing, the gas rate through the jet will influence its suction pressure. This is shown on the typical jet performance curve in picture, which is drawn for a constant discharge pressure of 100 millimeters of mercury. Let me make a critical comment about this curve. Variations in the jet's discharge pressure may have a surprising, that is, nonlinear effect on the jet's suction pressure. Sometimes, a small reduction in the discharge pressure will make a tremendous improvement in the suction pressure. The compression ratio might increase from 3 to 1 up to 7 to 1. Sometimes, a very large reduction in the jet's discharge pressure will not alter its suction pressure at all. The compression ratio might decrease from 7 to 1 to 3 to 1. It all depends on something called the critical flow characteristics of the jet. More on this subject in a moment. Measuring deep vacuums. For any vacuums better than 120 millimeters of mercury, or 25 inches mercury at sea level, an ordinary vacuum pressure gauge will not be accurate enough for technical purposes. An absolute mercury manometer, as shown in picture, is needed. All that is required to make this simple device is a length of glass tubing bent into a U-tube shape. One end is sealed, and the other end is left open. Dry, clean mercury is then poured into the open end. The closed end of the U-tube is easily evacuated of air by tipping the glass U-tube on its side. A little jiggling will work out the last air bubble. The overall length of the tube will be about 8 inches. The mercury should wind up about 1 or 2 inches high in the open end of the U-tube. To read the vacuum, the mercury level at the closed end must be pulled down by the vacuum even just a little below the top of the tube. The difference in mercury levels between the closed and open ends of the U-tube is the precise millimeters of mercury vacuum. Wet mercury will give completely wrong results. Jet malfunctions. Big Spring is located in the scrub desert of western Texas. Cold autumn mornings are followed by warm afternoons. The local refinery's cooling water temperature follows this ambient temperature trend. The vacuum tower in this refinery also seems to keep track of the time of the day. At 6 a.m., the primary steam jet is running quietly and pulling a vacuum of 12 millimeters of mercury. At 7:30 a.m., the jet begins to make infrequent surging sounds. It rather sounds as though the jet is slipping every 15 or 20 seconds. As the morning coolness fades, the surging becomes more frequent. The vacuum also begins to slip from 12 to 14 millimeters of mercury. Then, at about 9 a.m., as the surges have become so frequent as to be almost continuous, the vacuum plunges to 23 millimeters of mercury. By 10 a.m., the surging has stopped and the vacuum at the jet suction has stabilized at a 425 millimeters of mercury. Many, if not most, operators of large vacuum jet systems have observed this problem, but what causes it? Loss of sonic boost. Let's refer to picture. As the cooling water warms, the temperature of condenser number 1 increases. This also increases the condensing pressure. This raises the discharge pressure of the primary jet 1, as well as the pressure in the diffuser throat shown in picture. Higher pressure will result in a smaller vapor volume. And a smaller vapor volume will cause a reduction of the velocity in the diffuser throat. The lower velocity in the throat does not affect the jet's performance, as long as the velocity remains above the speed of sound. If the velocity in the throat falls below the speed of sound, we say that the jet has been forced out of critical flow. The sonic pressure boost is lost. As soon as the sonic boost is lost, the pressure in the vacuum tower suddenly increases. This partly suppresses vapor flow from the vacuum tower. The reduced vapor flow slightly unloads condenser number 1 and jet 2, shown in picture. This briefly draws down the discharge pressure from jet 1. The pressure in the diffuser throat declines. The diffuser throat velocity increases back to, or above, sonic velocity. Critical flow is restored, and so is the sonic boost. The compression ratio of the jet is restored, and the vacuum tower pressure is pulled down. This sucks more vapor out of the vacuum tower and increases the loads on condenser number 1 and jet 2, the secondary jet. The cycle is then repeated. Each of these cycles corresponds to the surging sound of the jet and the loss of its sonic boost. As the cooling water temperature rises, the sonic boost is lost more easily and more rapidly. The surging cycles increase in frequency to 30 or 40 per minute. The vacuum tower pressure becomes higher and higher. Finally, the surges become so frequent that they blend together and disappear. The primary jet has now been totally forced out of critical flow. The sonic boost has been lost until the sun in Big Spring, Texas, sets and the desert cools. Surging then returns until the critical flow in the jet is restored, and the sonic boost is regained at about 9 p.m. Restoring critical flow. Steam jets, especially the primary jets, are forced out of critical flow, most commonly because inadequate capacity of the primary condenser, that is, condenser number 1 shown in picture. Overloading or poor performance of the second stage jets. The problem at Big Spring was rather typical. The two parallel, second stage jets were not working as a team. Jet A in picture was a real strong worker. Jet B was a loafer. It is rather like running two centrifugal pumps in parallel. Unless both pumps can develop about the same feet of head, the strong pump takes all the flow, and the weak pump is damaged by internal recirculation. In the case of jets working in parallel, the strong jet takes all the gas flow from the upstream condenser. Furthermore, the strong jet sucks motive steam out of the mixing chamber in picture. As you can see in picture, the suction temperature of jet A is 20 degrees Fahrenheit hotter than the condenser number 1 outlet temperature. This could happen only if the flow of vapor in the jet B suction line were backward. Blocking in jet B stopped the primary jet from surging until the more intense heat of the late afternoon. When I block in one ejector that is running in parallel with one or two other jets, I always try to remember to close the large process inlet valve first. If you close the smaller motive steam valve first, then the discharge flow from the other parallel ejectors will recycle back through the jet you are removing from service. The vacuum will suddenly break. So, block in the steam valve second, and the discharge valve from the jet third. I've made the error of closing the steam valve prematurely, so you can be guided by my errors. Calculating sonic velocity. I have discussed in lecture the effect of reaching sonic velocity, also called the critical flow velocity or choke flow. To calculate sonic velocity, Vs in feet per second. Vs equals 223 square root of K times T divided by MW, where T equals degree F plus 460 equals degree R, MW equals molecular weight, pounds, K equals ratio of specific heats, Cp divided by Cv. K for ethane is 1.2, K for air and hydrogen is 1.4. For higher molecular weight components, assume K is 1.1. Sonic velocity is also referred to as choke flow. One characteristic of choke flow is that reducing the downstream pressure does not significantly increase the flow through the choke point. Increasing the upstream pressure increases the flow in a linear proportion to the absolute increase in pressure. A vapor-liquid mixture developing sonic velocity in a pipe will cause the liquid to atomize. The tiny droplets of liquid will then be difficult to settle out in a downstream separator vessel. This is often a cause for entrainment in vacuum tower feed nozzles. Effective gas rate. The most effective operating change to restore a jet to its critical flow mode is to reduce gas flow. As I have described, this reduces the primary jet's or jet 1's discharge pressure. Also, less of the energy of the motive steam is expended in accelerating the reduced gas flow. Hence, the steam enters the diffuser throat with greater kinetic energy. This also helps, along with the lower discharge pressure, in restoring critical flow and the jet's sonic boost. To reduce the gas flow from the vacuum tower, shown in picture, I cut the heater outlet temperature from 750 to 742 degrees Fahrenheit. This reduced thermal cracking in the vacuum heater and the consequent production of cracked gas. The pressure in the vacuum tower dropped from 21 to 12 millimeters of mercury, and production of valuable heavy gas oil from the vacuum tower bottom residue increased by 20%. I can still recall the warm afternoon sunshine on my face as I signaled to the control room operator to drop off that final degree of heater outlet temperature. I can still hear the last surge dying away as the primary jet recovered from its long illness. And as the jet began its steady, full-throated roar, I knew it was running in its proper critical flow mode. Reducing primary jet discharge pressure. Let's say that a jet is already in its critical flow mode. It is already benefiting from both the sonic boost and the velocity boost. What, then, will be the effect of a reduction in the jet's discharge pressure on the jet's suction pressure? Answer is not very much. If a reduction in discharge pressure is made on a jet that is not working in its critical mode, there will always be some benefit. But if the jet is already in critical flow, reducing the pressure downstream of the diffuser throat cannot significantly raise the flow of gas into the diffuser throat. I know, I've tried. Twice I have added a third-stage jet to an existing two-stage jet system. The discharge pressure from the second-stage jet dropped by 500 millimeters of mercury. The discharge pressure of the first-stage jet dropped by 160 millimeters of mercury. The suction pressure to the first-stage jet dropped by perhaps 2 millimeters of mercury. The critical discharge pressure for each jet is determined experimentally by the manufacturer. It is usually noted on the jet specification sheet. My experience indicates that exceeding this critical jet discharge pressure by the smallest amount will force the jet out of critical flow. Or, the way I see it, will cause the jet to suddenly surge a few times and then lose its sonic boost. The inverse is not always true. A jet with less than its critical discharge pressure may not pick up its sonic boost. Operationally, this business of gaining or losing sonic boost is a rather dramatic effect. Condensate backup. The jet in picture has a small, calculated compression ratio of about 180 millimeters of mercury divided by 150 millimeters of mercury equals 1.20. This extremely low compression ratio does not indicate any sort of jet malfunction. The high jet suction pressure is caused by the 140 degrees Fahrenheit pre-condenser outlet temperature. The vapor pressure of water at 140 degrees Fahrenheit is 150 millimeters of mercury. There is a large amount of process steam flowing into the pre-condenser. The lowest possible pressure that the pre-condenser can operate at and still condense the process steam is 150 millimeters of mercury. As the jet sucks harder, it just pulls a few more pounds of water out of the pre-condenser, without altering the pre-condenser's pressure. The problem with the pre-condenser is condensate backup. Something, perhaps a partially plugged drain line, is restricting condensate flow. As the condensate backs up, it reduces the surface area of the condenser exposed to the condensing process steam. This makes it more difficult for the process steam to condense. The condensate backup also subcools the condensate. The net result is that the precondenser vapor outlet temperature goes up and the precondenser liquid outlet temperature goes down. Recently, on a job, I was able to force a jet to surge and lose its sonic boost simply by raising the condensate level in its downstream condenser by just 6 inches. Lowering the level drew down the jet's discharge pressure by a few millimeters of mercury and restored it to critical flow. Condensate backup is also caused by a large number of problems associated with the barometric drain line, and especially with the seal drum, shown in picture. Air leak in drain line. This caused local chilling of the line near the leak. Likely, the intrusive air was mixing with the light liquid hydrocarbon in the line and promoting auto-refrigeration. Wax plugging in the drain line. Gas oil entrainment is often quite waxy. The cure is to steam out the drain line. Sludge buildup in the seal drum. The bottom of the seal legs were only 4 inches above the bottom of the seal drum. The seal drum overflow baffle was 4 feet high. I had the drum cleared and cut at 18 inches off the seal legs. Biological corrosion inside the seal drum. The bacteria metabolized H2S and iron in the warm seal drum aqueous phase to form the sludge. If the internal seal drum legs are made of carbon steel, should use 316L stainless steel, the internal seal drum legs will hole through and unseal the barometric legs. Running at very high liquid levels to submerge the hole is the temporary cure. False seal drum level indication. The level had been showing at dead steady 80% level for months. Actual level when I blew down the liquid level taps was 100+%. Too much naphtha in the vacuum tower feed made it impossible for the vacuum condensate seal drum slough pumps to keep the level under control. Turning on the spare pump did not help, as both pumps were operating on the flat portion of their performance curves. Jet freeze up. There is another type of jet surging, which is caused by the motive steam turning to ice. How is this possible? Certainly, steam cannot turn to ice inside the jet. But it can and does. The jet system was in Mobile, Alabama. The symptoms of the problem were extremely poor performance of the primary jet. The poor performance was constant, regardless of the cooling water temperature. The jet would roar along in a normal fashion, and then go extraordinarily quiet for 10 to 15 seconds. The outside of the mixing chamber would chill to exactly 32 degrees Fahrenheit during those times when the jet was quiet. This happened even though it was a bright, warm, sunny day in Mobile. Incidentally, the way to measure surface temperatures in the field is with an infrared handheld thermometer. The response time of these thermometers is infinitely faster than in old-style, contact thermometers. You can buy one from any good instrument catalog one for a few $100s. Naturally, if the jet freezes, steam flow will stop. The jet will be quiet, and its compression ratio will be nil. But what causes the steam to turn to ice? Well, a number of factors extract heat from the steam. When any vapor expands, due to a pressure reduction, other than H2 and CO2, it cools off. This is called a Joule-Thomson expansion. The reduction in temperature of the steam is called a reduction in sensible heat content. The sensible heat of the steam is converted to latent heat of condensation. Does this mean that the latent heat of condensation of 10 psig steam is much higher than that of 450 psig steam? Let's see. Latent heat of condensation of saturated 10 psig steam equals 980 BTU per pound. Latent heat of condensation of saturated 450 psig steam equals 780 BTU per pound. When the velocity of a vapor increases, some of the increase in kinetic energy is extracted from the sensible heat of the vapor. The steam also gives up some of its energy to provide increased momentum to the gas flowing into the jet suction nozzle, shown in picture. If the motive steam were dry, these factors would reduce the 150 psig motive steam saturated temperature from 350 degrees Fahrenheit to about 100 degrees Fahrenheit. But the motive steam in Mobile was not dry. It had partly condensed in the steam supply line to the jet. If steam is wet and contains liquid water, the water will flash to steam when the steam pressure is suddenly reduced to a vacuum. But the heat of vaporization comes from the sensible heat content of the steam. If the steam contains 10% moisture, it will chill by 180 degrees Fahrenheit on flashing. This implies that we could have the wet, motive steam temperature dropping to -80 degrees Fahrenheit as it enters the jet's mixing chamber. But, of course, the steam will turn to ice when its temperature drops to 32 degrees Fahrenheit. The ice blocks the flow of steam. As the steam velocity slows, the jet warms and melts the frozen steam, and the steam flow is restored. Wet steam. The problem in Mobile was resolved by installing a small steam filter on the steam line to the jet. This filter extracts moisture from the steam and blows it out through a steam trap. But wet steam is bad for a jet, even when it does not cause the jet to freeze. Mainly, wet steam causes erosion of the steam inlet nozzle. Erosion of this nozzle is the main reason why jets undergo mechanical deterioration. As the nozzle erodes, it allows more steam to pass through into the diffuser. The diameter of the diffuser is designed to operate with a certain steam flow. If that designed steam flow is exceeded, the diffuser operation suffers. Also, the downstream condenser pressure will also increase. An eroded steam nozzle shows no obvious sign of damage. The erosion is quite uniform, and the nozzle interior is smooth. The inner diameter of the jet must be checked carefully with a micrometer. Growth in diameter of just 5 to 10% is significant. The nozzle is intended to be replaced periodically, much like the impeller wear ring on a centrifugal pump. Steam ejector temperature profile. The motive steam, as it flows through the ejector, passes through three distinct portions of the ejector body. First, steam nozzle. Second, converging section of the ejector. Third, diverging section of the ejector. The function of each of these three sections is First, in the steam nozzle, the temperature, enthalpy, of the steam is converted to velocity, kinetic energy. Second, in the converging section, the velocity of the steam is used to compress the off-gas, air leaks, and the motive steam itself, due to the combined vapor flow exceeding critical velocity, the sonic boost. Third, in the diverging section, the velocity of the steam is used to compress the off-gas, air leaks, and the motive steam, due to the reduction in the velocity of the combined vapor flow, the velocity boost. The temperature profile is observed by monitoring skin temperatures with an infrared temperature gun. When I do this, here is what I've observed. First, if the motive steam is dry, saturated 150 psig, 360 degrees Fahrenheit steam, then the temperature at the front portion of the ejector body will be around 100 degrees Fahrenheit. The 360 degrees Fahrenheit steam temperature has been converted into velocity in the steam nozzle. Second, if the inlet temperature at the converging section of the ejector is 100 degrees Fahrenheit, then the temperature halfway along the ejector, at its throat or narrowest portion, will be about 200 degrees Fahrenheit. The ejector has been heated by 100 degrees Fahrenheit, due to the heat of compression of the flowing vapor provided by the sonic boost. Third, if the inlet temperature at the diverging section of the ejector is 200 degrees Fahrenheit, then the temperature at the discharge of the jet will be about 250 degrees Fahrenheit to 300 degrees Fahrenheit. The ejector has been heated another 50 degrees Fahrenheit to 100 degrees Fahrenheit, due to the heat of compression of the flowing vapor provided by the velocity boost. Sometimes the first portion of the ejector will be a lot colder than 100 degrees Fahrenheit. That's because there are several percent of moisture in the motive steam, which is bad. Sometimes the converging portion of the ejector will heat up by 10 degrees Fahrenheit or 20 degrees Fahrenheit, rather than by 100 degrees Fahrenheit, as it should. That's because there is no compression taking place in the converging portion of the ejector, which is also bad. Lack of a significant temperature rise, about 100 degrees Fahrenheit, across the ejector's converging section is a positive indication that the ejector is failing to develop its sonic boost. This is the principal malfunction encountered in troubleshooting steam ejector performance. The temperature profile I've just described will vary with vapor loads, air, cracked gas, vapor composition, molecular weight, ejector mechanical condition, steam conditions, moisture or superheat, ejector discharge pressure, as controlled by the downstream, condenser performance, suction pressure. I had observed a wide variety of temperature profiles of ejector bodies, and for many years I failed to understand the significance of my observations. After years of confusion, I decided to analyze the data using my education in thermodynamics. Muller diagram for steam. I find it strange that the engineering principles that I was supposed to have learned when I was 20, I only realized how to actually apply when I was well past 50. But now that I think about it, pretty much all of life is like that. I summarize this as a small 10 degrees Fahrenheit to 20 degrees Fahrenheit temperature rise across the converging section of a steam jet is a definite indication of the loss on the sonic boost and of a low ejector compression ratio. The overall temperature rise across the ejector's diffuser section should be 150 degrees Fahrenheit to 200 degrees Fahrenheit. Why, but it happens. I have learned a lot about how process equipment actually works by investigating comments such as, "It may not make any sense to you, but that is what happens here." Process equipment always conforms to the principles of science, but we have to get to know which principle to apply. Picture shows an old vacuum tower. The chief operator on this unit made the following statements. The colder the vapor outlet temperature from the precondenser, the better the vacuum that the ejector could develop, because of reduced vapor flow to the jet. Agreed. Increasing cooling water flow to the precondenser decreases the vapor outlet temperature. Agreed. Closing the cooling water outlet valve A, about 3/4 of the gate valve steam travel, increases cooling water flow through the precondenser. Nonsense. Really, dear gentlemen, How can closing a valve in a pipeline increase flow in that pipeline? It cannot, and it will not, and it did not. Yet, on the other hand, it is a really bad idea to disregard field observations made by experienced plant operators. So, let's take a closer look at picture. First, I tried opening valve A. Just as the chief operator said, cooling water outlet temperature increased, proving that water flow was reduced. Next, I checked the pressure at bleeder B. It was 12 inches of mercury. The pressure was so low at this point because of the 20 psi delta P of the cooling water as it flowed through the tube bundle. The 35 feet of elevation, about 15 psi of head pressure, that the water had to gain to climb to valve B. Of course, this 15 psi of head loss was regained when the water flowed back down to the cooling water return header. The first idea I had was that the 120 degrees Fahrenheit water would partially flash to steam at 12 inches mercury and the evolved vapor would restrict water flow. Wrong. The vapor pressure of water at 120 degrees Fahrenheit is 26 inches mercury, not 12 inches mercury. But cooling water is not just pure water. It is water that has been saturated with air in the cooling tower. Sure enough, when I calculated the amount of dissolved air that would flash out of water, which had been saturated with air at 90 degrees Fahrenheit and atmospheric pressure, I found that a very large amount of air could flash out of solution. It was just as the chief operator had said. Opening valve, too much evolved large volumes of air in the second pass of the U-tube pre-condensers, shown in picture. Certainly, the total volumetric flow through the outlet of the condenser does increase, as valve A is opened. But the incremental flow is all air, and all that air does is choke off the cooling water flow. Optimum vacuum tower top temperature. The chief operator also insisted that lowering the vacuum tower top temperature too much would hurt the vacuum. But why? There is no doubt that the colder the tower top temperature, the less the heat duty load for the precondenser to absorb. Hence, cooling the vacuum tower top temperature should, and did, reduce the precondenser vapor outlet temperature. This should have reduced the vapor load to the downstream jet. But it didn't. Here is why. The vapor components distilled overhead from the vacuum tower consisted of steam, cracked gas, and naphtha. The steam and naphtha vapors would pretty much totally condense in the precondenser, shown in picture. Some of the cracked gas would dissolve in the condensed naphtha. Most of the cracked gas would flow onto the jet. Increasing the tower top temperature would distill over more pounds of naphtha. The extra condensed naphtha would dissolve more cracked gas. The reduced flow of cracked gas to the jet would unload the jet and permit it to develop a larger compression ratio. Of course, if the vacuum tower top temperature became too high, the increase in the precondenser vapor outlet temperature would increase the vapor pressure of water. This factor would then limit the minimum pressure in the precondenser. In another case, a large volume of NH3 was accidentally injected in the inlet to the condenser. The vacuum instantly improved. Why? Well, the NH3 reacted with the H2S in the cracked gas to form ammonium sulfide. This salt is very soluble in water, H2S is not. The H2S was effectively extracted from the cracked gas, and the downstream jet was thus unloaded and sucked harder. Jets have been partially replaced by liquid ring seal pumps. These are really positive displacement compressors. The gas is squeezed between the vanes of the compressor's rotor and a pool of liquid in the compressor's case. Liquid ring seal pumps are not interesting. They have no character. They are not as complex as steam jets. Anyway, I will discuss positive displacement compressors in later videos. Measurement of a deep vacuum without mercury. Above 30 or 40 millimeters of mercury of vacuum, an ordinary digital battery-powered vacuum gauge is sufficient. However, only a vacuum mercury manometer is accurate in the 5 to 15 millimeters of mercury range. As long as the mercury was dry, such a gauge gave excellent results. I have developed an alternate method that works almost as well as the vacuum mercury manometer. It's really the same idea shown in picture. Fill the closed end of the tubing with baby oil and mineral oil. Make sure you get the last bubble of air out of the closed end of the tubing. Always use fresh oil to prevent moisture contamination of the oil. Fill the entire glass U-tube with oil. Connect the open end of the glass tubing to the vacuum pressure point being measured and open the connecting valve very slowly. The specific gravity of baby oil is about 0.9. The specific gravity of mercury is 13.6. Mercury is 15 times denser than baby oil. Referring to picture, divide the 150 millimeters of elevation difference in the manometer legs by 15 to determine that the vacuum is 10 millimeters of mercury. For vacuums above 40 millimeters of mercury, the oil-filled vacuum manometer is not practical, as it would be about 30 inches in overall length. Do not use lighter fluids than baby oil, as they will create a vapor pressure at the closed end of the glass U-tube. This will result in a measurement of a better vacuum than really exists. Water is also too volatile at moderate ambient conditions for this purpose. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.